So we'll talk about the following topics in neutrinos. First, about three neutrinos and methods of detecting them. Then we'll talk about neutrino oscillations. First in vacuum, and then in matter, then we'll talk about neutrino interactions. And finally, we will talk about atmospheric neutrinos, which are the most relevant ones for INO. And then, depending on the time, I may or may not talk about solar neutrinos and some neutrino mass models. Okay. So, in what context do you first hear the word neutrino? Beta decay. And beta decay is part of radioactivity, and you can say to some extent discovery of radioactivity is the beginning of modern physics, so to speak. And there were two important. First, of course, was the discovery of radioactivity itself, and the second important experiment was done by Madame Curie and her husband, where they observed the following interesting phenomenon. There is a mineral of uranium called pitchblende. And this pitchblende was more radioactive than pure uranium. So people realized that uranium salts, the original discovery was some uranium salt was emitting some radiation. But then when you look closely, and people managed to isolate pure uranium, they found that this uranium salt was more radioactive than pure uranium. So, what is that telling you?
Another ion is decay.
Means that you have to be more precise. See, I see that I have 1 kilo of uranium and it's giving off a radioactivity, I don't know, let's call it 1 microcurie. And this is 1 kg of uranium. And I take 1 kg of pitch blende, which I know contains maybe 990 grams of uranium, and it is giving off radioactivity 2 microcurie. So what does that mean?
This is more unstable as compared to the other.
Mean?
It contains some other element.
Yeah.
Might be more.
So this in 1 kg it is 990 grams pure uranium plus 10 grams something else. And based on this, what is the radioactivity of 990 grams of uranium? Well, yes, roughly 1 curie, 0.99 curie if you want. So the rest 1 curie, 1 microcurie, is coming from that 10 grams, which means that whatever that is at least 100 times more radioactive than uranium. So this was the conclusion drawn by Madame Curie and her husband, and they took it up as a challenge to isolate what this additional as yet unknown element is, which was emitting which was much more radioactive than uranium. And after a lot of effort, they actually found not one but 2 elements. What are they called? One was very imaginatively named radium, and the second one, Madame Curie, is actually born in Poland. So after her homeland, she named it Polonium. But one thing that neither Becquerel, who discovered radioactivity, nor the Curies did is, what is it that is coming out? So all they were doing is they were exposing photographic plates, and the photographic plate and whatever is coming out is hitting the photographic plate and leaving a sign. They didn't bother to study, or I should be more careful, at least they have not, their efforts were oriented towards this rather than to study what is actually coming out. Okay, people thought it's radiation, and of course you have all kinds of radiation: infrared, visible, ultraviolet. Then of course at that time recently X-rays were also discovered. But Rutherford, the same Rutherford of Rutherford experiment, he did this famous experiment where he put a small amount of radioactive element in a lead block with a hole drilled in. So whatever emission is coming out. On all other sides it is blocked and it comes out only through this hole. And then what did he do? Rutherford was a student of Thomson of the E/M experiment failed. So he measured the E/M ratios of the particles that were coming out. In particular, he applied a magnetic field here and found that some particles deflected this way and some particles deflected this way. Which meant some are positively charged and some are negatively charged. And then when he measured the E/M ratios, he found that the positively charged ones he called alpha particles, and they were the nuclei of helium, and the negatively charged particles, they are electrons. And people then started studying these things in more detail, and the alpha decay was a big puzzle. How come a readily made nucleus is coming out from a larger nucleus? So, and that alpha particle decay was explained by George Gamow using the concept of tunneling, which is one of the new things that quantum mechanics predicted. Before that, if you use classical mechanics, you cannot have a concept of tunneling, but it becomes a possibility in quantum mechanics. And this beta decay presented a puzzle. So you look at number of electrons as a function of energy. You take a radioactive subset and you observe all the beta decays that are occurring, and for each electron that comes out, you measure its energy. And initially the data looks something like that. Data, whenever you do a new experiment, the data initially is sparse, but that's how the data look. But you have a nucleus N1 decaying into another nucleus N2 plus electron. That is how we would write the equation for beta decay. Nucleus N1 has some given mass, and nucleus N2 also has some given mass, and energy of the electron should be the difference of these two masses. So the picture we have of beta decay, electron should come out with fixed energy, but you find that you have electrons coming out with some 3 or 4 different values of energies. One suggestion made was that maybe people didn't explicitly see this second nucleus, so maybe there are some 2-3 different nuclear states into which N1 is transiting. So they all have different masses, therefore electron is coming out with different energies. But as things improved, there were no such nuclear states observed. Another suggestion made was that maybe along with the beta decay, there is some kind of gamma radiation taking place, which the electron detector is not observing. If not gamma, some X-ray or ultraviolet rays are being emitted, and people actually built calorimeters which would catch any such extra energy that was emitted, and found that no such extra energy was emitted. And also the beta decay data improved, and it started looking like this. I mean, these are all discrete points, but the pattern certainly looks as if this electron energy is a continuous variable. That means it looks as if energy conservation is not valid in beta decay. And in fact, I believe Niels Bohr even made a suggestion that energy conservation is a macroscopic concept, just as a lot of classical concepts do not apply in quantum regime. Maybe energy conservation does not apply in quantum regime. However, Pauli was not willing to accept that, and the reason is you have theorem is very simple to state and prove that for every continuous symmetry there is a conserved quantity, and for every conserved quantity there is a continuous symmetry. And so according to Nasa's theorem, time translational invariance of a theory leads to energy conservation, and energy conservation implies time translational invariance. And you can't do physics unless you have this symmetry. Your theory has this symmetry. This means if I do an experiment today, I get some result. I do the same experiment tomorrow. This symmetry guarantees that I'll get the same result tomorrow also. If you don't have that guarantee, there is no way you can do physics. So, giving up on energy conservation is equivalent to giving up on time translational invariance, which means you should stop doing physics, and Pauli was unwilling to do that. So he made this radical suggestion that there is a additional particle being emitted in beta decay, and that is escaping detection. By the way, if you have read any stories about history of physics, especially history of development of quantum mechanics, you know that Pauli is a very brash individual. Supposedly, when he was a student at the University of Munich, Einstein went and gave a talk sometime in 1921-22, around the time Einstein got his Nobel Prize. And at the end of the talk, Pauli is supposed to have commented, "Oh, what Mr. Einstein said is not entirely stupid," some such thing. But he hesitated to publicly announce this idea of a particle which cannot be detected. It's like saying there are ghosts. In the middle of the night, you hear some strange noises. You try your best to find the source of your noise, but you can't. So you say, "Oh, the noises are coming due to ghosts." But he did want to advertise the idea, so he wrote a letter and gave it to a friend who was going to attend a conference on radioactivity, and asked his friend to read that letter at that conference. And in fact, if you Google "Dear Radioactive Ladies and Gentlemen," you will see that letter. And so where he announces this idea that there is a third particle being emitted in beta decay, which is carrying away the rest of the energy, and therefore energy conservation is valid in beta decay. And I don't know how many people took the idea seriously, but fortunately for Pauli, one very smart man, that is Enrico Fermi, took the idea very seriously, and he actually constructed a theory of beta decay based on Fermi's idea, based on Pauli's idea. There are two versions of beta decay, Fermi's theory of beta decay, one non-relativistic version and one relativistic version. I will discuss the non-relativistic version, and I urge you to look up the relativistic version in one of the textbooks. So the basic point is we have N1 going to N2 plus electron plus neutrino, and energy conservation means that M1 is equal to M2 plus energy of electron plus energy of neutrino, or equivalently energy of electron plus energy of neutrino is M1 minus M2, which we call Q. By the way, we use what are called natural units, where we set C equal to 1. Of course, Fermi was able to construct his theory of beta decay because he also has derived what is known as Fermi's golden rule, which is applicable not only in beta decay but for all decays, and not only decays, all kinds of atomic transitions. And the argument goes like this. I have N1 with energy M1 and of course momentum 0 going into okay, let me write it in a different way. First, let me write down Fermi's golden rule. This is for the non-relativistic part of version of Fermi's golden rule. Relativistic version is a little more complicated. So I have some well-defined initial state I and a well-defined final state F, and I want to calculate the transition rate d gamma from I to F, and this is the transition matrix element mod square times delta E final minus E initial, which guarantees energy conservation, times the element of phase space. Actually, 1 minute. Before I go to phase space, let me write this as, yeah. This is Fermi's golden rule. This R implies rate of transition. And dimensionally, Hamiltonian has dimensions of energy, so it works out because we have, this is energy square, this has dimensions 1 over energy, so this whole thing has dimensions of energy, and the rate is inverse time, which has dimensions of energy. Yeah. Now, in order to be able to do this calculation, we need to know this matrix element. First, let us write down that matrix element. What is my initial state? Initial state is the nucleus N1 with energy M1 and momentum 0. That is my initial nucleus. My final nuclear state, my final state is with energy M2 and momentum essentially 0 times electron with energy E, momentum K1 times neutrino with energy E mu, momentum K2, or I'll call Ke and K. We call it Ke and K. this is my final state. And I need to find this matrix element. Okay, I know what the initial state is, I know what the final state is, but in order to find this matrix element, I need to know what this H interaction is. And Fermi had no idea what it is. So, in such situations, you and I will give up and find something else to do. Fermi, of course, being a genius, made a genius-like assumption. So, we have no idea what it is. I ask you to take a guess, the simplest non-trivial guess you can make. So, what is the simplest non-trivial guess you can make about this matrix element? Trivial guess is it is 0, but if it is 0, the rate of beta decay is 0, and obviously it's not 0, so trivial guess doesn't work. So, what is the simplest non-trivial guess you can make? No, I'm considering a matrix element. So my initial state is fixed, final state is fixed. I'm not asking about guess about Hamiltonian. I'm asking you to make a guess about the matrix element. Simplest non-trivial guess you can make. See, typically all these matrix elements, they involve all kinds of kinematical variables. There you make, but I'm asking you to make a guess about it. Simplest possible guess. No, you are thinking in terms of matrices. I'm asking you, this is just a number. It's a matrix element.
It's a constant.
Well, 1 is nearly correct, but the guess is you assume it to be some constant. Independent of all kinematic information there is. People have been measuring a lot of the decays in atomic physics. And in all those decays, the matrix elements do involve, they are functions of initial energy of the initial state, energy of the final state, ... But all that information, based on that, people inferred what this interaction Hamiltonian is. But here, there is no information, either from experiment, we only know that there is a continuous spectrum, nothing more. And theory, there is nothing at all. And Fermi was trying to develop theory. And he was compelled to make a guess, and he assumed that this is a constant. And next step is fairly straightforward. I have taken trouble to explicitly write out the final state, but this is one possible final state. There could be many possible final states for which this constraint is satisfied. So to calculate the total rate, I have to sum over all the possible final states for which this constraint is satisfied. That is equivalent to integrating over all the electron momenta and integrating over all the neutrino momenta subject to the condition this is satisfied. If we are doing relativistic theory, we also impose momentum conservation explicitly, but while doing non-relativistic theory, we make an assumption that momentum conservation is somehow satisfied. So actually Ke vector plus K nu vector will not be zero. Typically they have a non-zero value, and that momentum actually is taken up by this nucleus, but the mass of this nucleus is much more than that momentum, so we can afford to ignore it. So with this, yeah.
E8 and EI.
Yeah.
Nuclear energy levels.
Yeah. No. EI is M1. EF is M2 plus EE plus E nu. Energy of the complete final state. So when I do that, we get d gamma is equal to, I'll put some g tilde here. You see the reason why in a minute. G tilde square times delta, or I will write here explicitly, E plus E nu plus M2 minus M1 B cube K nu B cube Ke. I integrate over all possible electron momenta, all possible neutrino momenta, and if I do so, you find that the dimensions are not quite coming out correct, but don't worry about it. The reason is there are other factors I should have put in to get the normalizations correct, which I have not put in, but the final formula, things will be taken care of, and you will find the final formula is dimensionally correct. And this d cube K nu I write as, I'm not measuring the direction of, I'm not measuring the neutrino at all, and I'm not measuring the direction of the electron. So this I'll write 4 pi K nu square dk nu and 4 pi K square dk. And these 4 pi factors and these 2 pi by h cross factors, everything I will absorb into this constant, and I will write as d gamma is equal to g square times delta E plus E nu minus Q. M1 minus M2 I have said is Q, we define it. So times d nu square d nu Ke E B. So in writing this, I have used the following for neutrino. For electron we have E square is it, just check if it is visible. This color is slightly different. Oh, I think this is white chalk only, so let me use yellow chalk. So we have E square is equal to P square plus ME square, which implies EDE is equal to KE. And for the moment I am assuming neutrino is massless, so E nu is equal to P nu, and I have made the appropriate substitution. And as I said before, we are not detecting the neutrino, therefore we should integrate over all the neutrino energies, subject of course to this constraint. So if I do that, I have d gamma is equal to G square, and wherever I see E nu, I replace it by Q minus E times E, and this KE is root O. You have to excuse me, I have suddenly shifted notation from K to P. Sorry, this should have been, I should have written it as KE square and K nu times E square minus ME square. This is d gamma dE. And now let us plot this function. So when EE is ME, because of this it is 0, and when EE is Q, because of this factor it is 0. So it is 0 here and it is 0 here, and if you plot it out, it will have some shape like other way. There is a quadratic dependence here, so the rise is slow and the fall is sharp. Will have some shape like that, and which is exactly what we see people who did beta decay experiments observe. This is and from this I calculate gamma, which turns out to be g square times some function of q. If I integrate out the electron energy, or I should say to be in q and me, and so for a given nuclear decay, I know the value of q, and of course I know the value of electron mass. So I evaluate this function, I compare it with the measured decay rate, and I get the value of g square. And also consider here the g square is cancelling out, and I have this 1 over f of q comma me, q minus e square e root e square minus me. So now the right hand side depends on only known things, no unknown, no strange factors. And by the time Fermi proposed this theory, I don't know how many different beta decays have been observed. I would imagine probably hundreds. So you have something like 100 beta decay spectra. For each of these, experimentally, you construct this quantity. You have measured d gamma de, and you add up, you get gamma. So you normalize your d gamma de with gamma. So the left hand side is a purely experimentally measured quantity, and the right hand side depends on a universal constant, electron mass, which was very precisely measured, and for a given decay the corresponding q value. And you take the data from these 100 experiments and you compare, and it was found that in every single case there is a good match between the theory and the data.
Sir, how do you write that gamma is equals to g square?
Huh?
I didn't follow.
Sorry?
Gamma is equals to g, that.
This one? Well, I need it. I mean, hello. You look at this. I integrate over all the electron energies. So right hand side is some function of q, and then I have integrated over with respect to electron energy. That's all. And I did that so that I can mod out this g square factor in this ratio. I can mod out the g square factor, and now my right hand side depends on two fixed things, q and me, and the variable e. And I compare this expression with the data I have taken for nucleus 1, nucleus 2, nucleus 3, dot dot dot. And in every single case, we get a good match between theory and data. So this is, you can say, is the indirect proof that there is indeed a neutrino. It is still a ghost particle, you can't detect it, but I can infer its existence by the missing energy. But I'm saying that I can infer its existence by its missing energy is a what we call a qualitative statement. Here we quantified it. Okay, it is taking away energy, only so much energy, so that E plus E nu equal to Q. What is the proof of that? If that hypothesis is correct, then the shape of the spectrum is predicted by this formula. Is that true? You go and verify it, and we find that it is indeed true. So we say that there is precisely one particle which is taking away energy so as to exactly conserve the total energy, that is E plus E nu equal to Q. Yeah.
Can there be more than one particle?
In principle, yes, but then shape will be different. You will not get this kind of shape. And I mean, if you want, you can play around with it on a computer to see if what are the momenta. I mean, you know what Monte Carlo is. I mean, you know how to randomly assign things. So you can you assume that there are 3 particles and sum of their energies is constant, and then you randomly assign momenta so that the vector sum of the momenta is 0, and then you try to calculate the shape of the energy of particle 1, which is what you detect. Particle 2 and 3 you are not detecting. So you play that game and see what shape you get. Yeah.
How did Fermi know that neutrino has very small mass?
Well, Fermi didn't know.
But
Yeah. I mean, here I have assumed so that I can get a simple expression. But I'm guessing here. I have not read Fermi's original paper. Let me confess that. But it is assumed, not, I mean, based on sort of some, you can say, gut feeling, so to speak, that the typical Q values are like MeV. So if the neutrino has a mass, it cannot be greater than mass of electron. That people understood very early on. But there are actually nuclei where Q minus Me is of Ke. So if the neutrino had a mass, its mass actually has to be much less than electron mass. That was also understood fairly early on. So it can be non-zero, most definitely. But in the first set of comparison you do, you set neutrino mass equal to 0. But what you said is what I'm going to do next. So, why should we believe neutrino mass is 0? So, we assume neutrino mass is non-zero, then I have to write E nu square is equal to K nu square plus N nu square, which means E nu d nu is K nu dk nu, and so d gamma is G square root of E nu square minus N nu square E nu d nu root of E square minus me square E d times delta E nu plus E minus Q. And now my d gamma dE will be G square times, previously I had Q minus E whole square, but now I have Q minus E times square root of Q minus E whole square minus M nu square E root of E square minus M nu square. So I get a more complicated looking formula. Now let us plot this formula. Or okay. So and previously I said the figure looks like this, but now you see that if E is close to Q, then I find that this thing will become 0 not at Q but before Q. So if the neutrino mass is non-zero, the endpoint of the spectrum is not Q but it will be so obviously this gives us a very nice way of measuring neutrino mass. So the name of the game is to find highest possible energy electrons. Trouble is, at this point rate is exactly equal to 0. So there is actually, you will not find any electron of that. So what you need to do is you have to make the measurement at a slightly lower value of E, where there is a non-zero rate, and extend it, do the extrapolation. Of course, with this formula as a guide. And at least from 1952 onwards, that is nearly 70 years, people have been doing these experiments, and in doing so, they invariably use tritium as the initial nucleus, which has a lot of advantages. One of the most important thing is this, the Q minus Me is 12 keV for tritium, which is one of the lowest values we have, and tritium is moderately abundant, so that I can have a large initial sample. And people have been doing experiments with tritium, I believe, since 1952, and so far there is only an upper limit on mu, no exact value, no non-zero value, and the latest number which came out just a couple of months or so ago, so the previous number which came in 2006 was from an experiment which took place in a German city called Mainz. They set an upper limit mu less than, I think, 2.2 electron volts, and then the next number came only 13 years later. The reason was people decided that they will try to build the ultimate beta-decay experiment possible, which took a lot of effort, and fine-tuning the detector ... So this experiment is also in Germany. It's called Neutrino, located in Karlsruhe, and just last month they announced a factor of 2 improvement, but they are continuing to take data, and over the next 5 years or so they expect to either find a non-zero value or push it down to 0.2 electron volts. And 0.2 is a sort of an important number, because later we will discuss from neutrino oscillations we have evidence that we should get at least 0.05. So in that sense, if you push it down to 0.2, then you are approaching the theoretical lower limit, and then if this experiment actually pushes it down to 0.2, then you really have to think of some really super experiment which will go from 0.2 to 0.05. And there are also cosmological arguments which say that, which prefer neutrino mass of about 0.1 to 0.2 electron volts. So all these things were taken into account in the design of Catherine. So the design is such that they will push this number down to about 0.2. But they've released their first results about a month ago, and they have set an upper limit of 1 electron volt.
So how many years experiment is this? Like how many years data will be taken?
I strictly speaking, I don't know, but I guess at least 5 years, and given the effort which went into making the detector, they'll probably try to push it even further. I mean, for example, look at LHC. It has now run for 10 years, but given the amount of investment that has gone into it, they are trying to push it to. Originally, they said, okay, it will run for 15-20 years, but now they are thinking of running it for 30 years. So, I believe initial plan is probably to run it for maybe 5 years.
This 1.1 ED is after how many years of data?
Oh, this is like months of data, 3, maybe 6 months. Okay, I will stop for today, but I want you to do 2 exercises. Or actually, so you forget about the G in the D gamma, that's just a normalization constant. You take Q to be 1 could be MEV, but and ME take to be 0.5, and I want you to draw three plots. So basically I want to see three plots like this, showing the behavior near Q for mu equal to 0 and for mu not equal to 0.
The red line is not.
Okay. but you have to be careful when you draw the figures. In this case, you can choose your x-axis to go from 0 to 1. It will be fine. But in this case, if you choose the x-axis going from 0 to 1, where would 1 minus 10 power minus 3? You can't make a distinction. So, in drawing this, you have to choose your axis so that the behavior near the endpoint is clearly visible. So, you should choose your x-axis to be EE going from, let us say, 0.99 to 1. So that 1 minus 10 power minus 3 will be visible. And similarly here, you have to choose EE to be 1 minus 10 power minus 5. And you should, in choosing your x scale, appropriate this sets your x scale, and of course correspondingly your y scale will also change, and you should set it appropriately. Important thing emphasize is behavior near the endpoint should be clearly visible. That's the thing. And you should see the distinction between m nu not equal to 0 and m nu equal to 0. So Cartering is here now, and you can imagine if you see this figure and compare it with this figure, you would understand the effort that went into designing of Cartering.